All right, so the notion of emergent information and strata connectivity, that is connectivity between strata, is the core principle of emergence theory, and it's also really the core theory of complex systems theory in general, which is, a lively branch of modern physics. So this is where ultra-complex things are causally connected to irreducibly simple things, always acting back upon those simple strata and the strata above. So quantum gravity via quasi-crystallographic graph theory uniquely allows fundamental graph connections to have mathematical first principles-based non-local relationships across time. Because of course you could make any arbitrary graph theory and plug, right, by non-first principles your non-local connections. But with quasi-crystal mathematics, we have no choice because it's served to us by geometric first principles that ultimately can be reduced to the Pythagorean theorem at the end of the day in trigonometry. So we can eliminate one dimension. We're trying to eliminate infinities, remember. So we've eliminated all of the local neural network theories, right? Even though it's possible that we shouldn't eliminate those. But we're going to eliminate those just to get started. And then we're going to do some dimensional elimination. We're going to eliminate all the theories in 1D because we think that reality is greater in its self-referential symbolic form is greater than 1D. And we're going to eliminate 2D for similar reasons, but less obvious. So it's easy to do this, less obvious to do this, but we're still going to eliminate this for now. And there's an infinity of quasi-crystals in each of these two spaces. So we have to be in quasi-crystals because it's the only known, at least known by me, example of a topological quantum net by geometric first principles, or by any first principles. And so we're eliminating these two dimensions. So to repeat, the reduction of letter types, or lengths, drives the increase of average valence rank, thereby increasing the connectivity power of these non-local codes relative to a metric which is defined by the fundamental lengths themselves, which we covered. Now, I said to repeat, but that's because there's a slide later, because we're talking about trans-temporal feedback loops. So there's a slide later that I've explained this, because here I didn't explain to you yet why the reduction of letter types drives the average valence rank, and I will later. The coalescing of all of these ideas from symmetry, again, we didn't discuss symmetry because I rearranged blocks, but symmetry is going to be a way that we're going to reduce another infinity, several infinities of possible quasi-crystal graphs that do not have H3 or H4 symmetry. And we'll talk about why those two symmetries reduce an otherwise infinite set of quasi-crystals, which can be derived from arbitrary irrational rotations of your projection window. So the coalescing of all these ideas from symmetry to non-locality to the density of E8, which is a thing we're going to talk about later, to the metric of volume that I showed you for, or the method for measuring connection density relative to dimensional density leads us to the following suggestion. The principle of efficient language and Noether's second theorem imply that nature uses either the QSN or the Elser-Sloan quasi-crystal. They are the logical candidates for the most efficient codes that nature can use because in the universe of quantum networks, that is non-local graph drawings as quasi-crystals, these two are the only logical candidates for highest connection density rank. The so note that I will end this presentation soon, in 400 more slides, with deductive arguments of what efficiency means in this context. We're going to talk more about that, I guess. So let us discuss efficiency, quote unquote efficiency, okay? In order to consider that word, you have to understand, you have to decide really on two things. you have to decide, well, what is it that is being conserved? What is it that you're trying to be efficient with? Is it money? Are you efficient with your money, energy, binary operations, and some better compression algorithm that's shorter? What is it? And two, what is it that you're purchasing with this thing you're trying to conserve? Are you trying to purchase like some physical representations? What is it? So more specifically for codes that simulate or represent something, what exactly is the pattern or the information one is trying to express in some spatiotemporal code, such as the class of codes that we're talking about. So long story short, we're going to decide on what the conserved thing is, and I think you know what it is because we talked about it. It's connections or points. It's points on-off, or it can be connections because the points being on-off define your connections by near-neighbor rules.
No, for me, connection is what you purchase, what you get. Point is what you have.
Well, I've explained this already. So there are two alternate ways, and I didn't suggest which way is better. If you have near-neighbor rules. So once you turn some points on or off, you may have a definition that it gets automatically connected to near neighbors that are either 1 or 1 over the golden ratio. And in that way, you can define your connections by turning certain patterns of points on or off. Or you can not work with points, and you can just work with connections. It may be the same way.
A third way. I'm working with point, but I don't put the point on or off. I have a grid of point, and this is what is conserved. I have used my money to buy this grid of point. So the less point possible. And then I want a maximum number of first neighbor connection, saying that if 2 points in my grid are at one distance, one length, then automatically they are connected. And what I want is to have the highest connection for the less points.
Okay, it's different than what I'm thinking because.
But it gives the same result.
Well, yeah, but you're using the words differently, just so you know. But so your conserved thing is not the points. That's the underlying possibility space. Your conserved action is some action on the point set, and that's conserved. Like for example, on infinitely large Penrose tiling, or some sufficiently large subspace of the Penrose tiling, you're going to have pretty much the same number of connections. The connections are conserved, even though you rearrange the connections differently.
Well, then the density would be the density will be the same if the connections are the same.
They are, yeah. The density is the same, and each connection is expressing a unit of curvature. In the projection of E8 to 3D, every one of your connections is simply an E8 root vector that expresses a unit of one-dimensional spatial curvature as contraction.
Okay.
And so that's always conserved. The global magnitude of curvature in every frame that's legal is always conserved.
So for each quasi-crystal has an efficiency, or it has a density, therefore it has an efficiency. And then another quasi-crystal would have a less density and then less efficient.
Yeah, if it has a lower average valence rank, for example, and relative to the dimension. So the conserved thing is some quantity of these actions, which are your connections, can be your connections, and then so you want to see, all right, well, what's the best pattern, the most physical pattern that achieves my physics that I'm trying to simulate for n connections, some fixed number or conserved value of connections. All right, so clearly the second question here is trivially clear. We're just trying to simulate physics. That's what we're trying to buy with our money. I just want patterns that simulate physics with some approximate resolution not to exceed the Planck length. And some time not to exceed the blurry probabilistic, and the Planck length and time, right? We don't need to go below that. And we don't need to go below probabilistically. We're allowed some blurriness. So we're allowed to go all the way up to the probabilistic jitteriness or approximation of precision that quantum mechanics defines. So that's our objective. That's what we're looking for, a conserved quantity of graph actions in some formalism to buy for our conserved quantity. So now I've tried to define, lead us to talking a little bit more rigorously about the word efficiency. So now we can take the quotation marks off of efficiency and talk about it. So a non-local quasi-crystal graph drawing code at the Planck scale might work for what we're trying to do, right? This is graph theory, the theory of connections. So note that one can think about this in two ways, and both of them are binary. You can turn your points in the possibility space on or off, and then once you have a set of points on or off, you recognize connections between near neighbor points when those distances are 1 and 1 over the golden ratio, or you can just leave all your points on, and you can just turn your connections patterns on or off. So you can deal with connections on or off or points on or off. Either way, you got to generate your connection patterns in 2 or more frames in these animations. However, note that when we use points as our binary actors, some points being on can generate rather large sets of connections. So you can get you might get more bang for your buck with binary actions of points than edges, because if I connect an edge, that's all I get, is just one connection. But then again, I may be getting a connection, with a large set of other connections if I'm connecting to, say, a degree 60 vertex. But if I'm connecting if I'm on-offing my edges, I got to turn every one of those 60 on. That's too many actions of my binary actions. So it seems that this points are an interesting thing, vertices. So, for example, when the centroid point of a 20 group is turned on, it can automatically generate 60 connections to it, in addition to a forced additional 60 additional connections on the outside edges that must be connected if the inner 60 are connected. And that's because we force our formalism for efficiency purposes, according to the PEL, to work with connected groups of 4 equidistant points. So it's a graph. It's essentially the complete and undirected graph represented in 3 space of 4 objects, the equidistant relationship of the 4 points. So when we do that, we get 6 connections for turning on 1 trit, but trits have a right and a left component in the QSN. So if you think about a 20 group centroid being turned on, well, those outer 60 edges come in 2 sets of 60. The 60 that describe the right twist and the 60 that describe the left twist. So you wouldn't know that, whether it's right or left, by just turning on the center point. So there are various other, I don't want to commit to any ways to do this, whether it's trits, edges, points. There's a lot of different ways you can do it, but what you want to think about is what would be the most efficient way, where you're taking actions as your conserved quantity, selections, choices, and then seeing how much pattern you get. So one can use a shift vector as the conserved value, and then you can ask, all right, well, how many connections does this computationally simple operator in the hyperlattice give me in this particular hyperlattice that I'm using, and then the sub-quasi-lattice possibility space that it projects to with state selections, versus a similar shift vector operator in a different system. And you can start looking for those which give you a lot of bang for your buck. And that's where E8 starts getting interesting, because E8 is in some sense the densest network. There's a lot of ways we could say it, but the most agreeable way is that it's the densest packing of 7 spheres, of course, in R8. So we can also use trits as equidistant sets of these on-off points with 6 connections automatically turned on with each trit tetrahedron. But just for today, in order to explain the concept of measuring efficiency in this context so that we can start eliminating more infinities of these types of codes, let's consider just points as being turned on and off in this non-local quasi-crystallographic graph drawing. Okay, and let's say we have 100 points that we can turn on or off according to the rules of some particular quasi-crystal code. And we have, for example, 100 frames. So in each frame, you're going to turn on and off. You're going to make a selection of state selections on 100 points in the possibility space to be on or off. And then you get to do that, repeat that 100 times, 100 frames, in order to simulate some very small physical system over some very short duration. So we don't know where yet these 100 binary actions in this ordered set of 100 frames is, because we haven't said. I'm not saying it's the QSN. It could be on the Elser-Sloan quasi-crystal, could be on the QSN or some other network. But we do know from the PEL that it must generate the most connections for our binary money, because connections is the name of the game in neural network theory, in graph theory, in graph drawing theory.
But I saw that you said it's a constant.
What is the constant?
The average.
Comparing different ones. So I'm saying we don't know yet what this system is. We're trying to eliminate infinities of possible quasi-crystal systems.
Oh, so you want to select a quasi-crystal that has the most connections. Okay.
The highest density of connection.
Well, yes. Not just the highest, the highest density, Cynthiana, that's right. Because
average rank, which is the same thing.
Yeah, the highest density because you want to get to the most expression of pattern for the least amount of irreducible choices or actions, and that is just going to inevitably be the one with the highest density, because you're painting all your physical pattern with connections. So, and it must comport with Noether's second theorem and modern expansions of her theorem, such as the standard model of particle physics, with its gauge symmetry mathematics. This code, right? The codes that we're going to select. It must possess the necessary high regular symmetry, okay, which is H3 or H4, right? That's the high symmetry. That's regular. In R3 and R4. And it must possess the necessary, okay, so let us compare the QSN to the Elser-Sloan quasi-crystal. Most of you guys understand that there are no analogs of the high symmetry regular polytopes in dimensions greater than 4. So you have H2, H3, H4. So those are the icosahedral symmetric kind of analogs, the 4D icosahedron, the 2D icosahedron, and then the 3D, right? And that's a very short series. That series spans from 2D to 4D, and then it ends forever. And then after that, your only regular polytopes forever are just the cube, tetrahedron, and octahedron. And they're hyper analogs. So we have a reason to believe that the Elser-Sloan has the highest average valence rank of a non-local net or quasi-crystal in any dimension, higher than the QSN. And we have reason to believe that the QSN has the second highest in any dimension with these qualities. It has to be H3 or H4. It has to be a non-local net. So let's compare the QSN to the Elser-Sloan quasi-crystal. Let's compare these two things. So we have reason to believe so then why would nature bother with using the QSN at all? Why, we believe that the Elser-Sloan quasi-crystal has an average valence rank of about 57.5. And we can kind of see now that the QSN has a lower average valence rank, all right? Because I will argue that the QSN is more powerful for 3 reasons. Number 1, for every connection pattern, there is a mirror opposite. The connections in the right-handed 20 group are different connections than in the left-handed 20 group. So a relationship between two 20 groups in the QSN can be RR, LL, RL, and LR. The analog of two 20 groups in the Elsner-Sloan quasicrystal has only one combination. And combinatorics, of course, are important with codes. There is a numerical and geometric coding scheme in the QSN which comes from the inability of tetrahedra to tile a two-sphere. This is geometric frustration. This is the 3-5 periodicity of helices that we explained in our Borgeter-Coxeter helix paper. And all helices in the QSN should have this 3 and 5 periodicity, regardless of whether those helices are made of 20 groups or helices of tetrahedra or helices of other supercells. This code will likely allow the code that we have to figure out, right? Because let's be clear, we don't know the code on the QSN right now. We don't know it. We know things about it, that it relates to cut plus projection, and that relates to this space of AB equals P tensor network operations. But we don't know the code yet. But I think that the code will allow syntactical freedom to alter in some helix. Remember, these particles are moving in helical patterns. So I believe it will allow syntactical freedom to alter the 3 and 5 periodicity of the helices. And that 3-5 can encode information. What information can it encode? So each Fibonacci chain, which is a geometric object, whether based on, so whether based on 3-5 periodicity patterns of helices or just in terms of lengths, so is isomorphic to a Fibonacci word, which is a string of zeros and ones where for example, your long in the Fibonacci chain quasicrystal becomes 1 and your short becomes 0. So then you have patterns numerically of long and short in Fibonacci words where every Fibonacci word encodes a unique integer. And in the QSN, our Fibonacci words are probably long, and so therefore encode large, unique integers. And integers carry information. A lot of information, can carry all sorts of information, of course. For example, in any integer carries its set theoretic combinatorics embedded within it, such that large integers contain exponentially more information than small integers. And one may decompose this entire discussion to the sum of the quantity and magnitude of the large integers that some non-local network like this can encode, where you can reduce it down and say, well, how many different Fibonacci chains, right, in numerical form or in length form, how many large integers can this code encode? So this is true because the densest connection network will, by its construction, have the highest density per large volume of Fibonacci chains and Fibonacci words. I hope that makes sense.
Well, the density is per large volume, so the density is already per volume.
Yeah.
It just needs to
Right.
be convergent for large volumes. I have a question before we move forward. How is the inability to tell a two-sphere related to efficiency?
Well, in 3D with respect to tetrahedra is unique because they can't tile certain spaces such as a two-sphere, and this is very powerful for code theoretic purposes, especially in the way that we discovered over the 9 years, and we have a way to trace all of that back up to E8. And this is the nature of the QSN, where the deepness of the QSN, because we could have just taken the E8 lattice and projected a slice of that lattice to R3. And in R3, we would get 7 + 1 contractions of the root vector units in E8, 7 of them having a Dirichlet integer value expressed with the golden ratio, each a different length, and each length encoding a certain magnitude of spatial curvature. And then the 1 is the compression of a root vector to 0, to a point. And so those 7 plus 1 expressions of spatial curvature, or even gravity, if you want to call it that, are the paints of your ability to paint with. But we want to reduce the number of paint colors because of the idea that an otherwise equal code with 1,000,000 symbols versus an otherwise equal code with 2 symbols, the second case is a more generally powerful code. And when we reduce the symbols from 7 to 2, it has a lot to do with geometric frustration. So what we do is we take our slice out of the Elser-Sloan quasicrystal where the tetrahedra are regular, and then we use a clone and repeat and rotate process to bring the QSN into H3 symmetry, which can be mapped back up to the Elser-Sloan. And by doing it in this way, in other words, the curvature needs to be expressed. So normally with projection, it's expressed by the edge contraction from 8D to 3D. But in this analog, called the QSN, we force, it's like pressure. So you force the expression of curvature. It has to express its information. So you pop it out. You force the curvature to be expressed instead of 7 edge contractions. By reducing it to 2, you force the information to be expressed as rotation and translation. Okay?
So basically you're saying that with that forbidden packing, sort of, you're forcing the symmetry, but it has nothing to do with increasing the density of connections or increasing the number of connections.
And it does have to do, no, it has exactly to do with increasing the connections, because when you project a 20 group, say from Elser-Sloan to R3, you get exactly an icosahedron. So at the center of the icosahedron is a vertex in the projection of the 20 group to 3D. And each of those vertices at the center of the icosahedral object, which is the projection, it is connected to the 12 vertices of the icosahedron. So that's a valence rank of 12. So you get 12 connections. But when you force the tetrahedra to be regular and you represent it in the twist isomorphism instead of the edge contraction isomorphism, and we formally dealt with that in the paper Fong did and Richard, then you have a binary arbitrary choice. You can have that spatial curvature represented in the form of the right twist, where 60 edges on the outside have 60 connections. And then if you arbitrarily choose it to be in the left expression, this binary choice, then the 60 connections on the outside are a different set of 60 connections. So you have a 60 plus 60 plus the inner 60. So it is exactly the way we deal with geometric frustration, by forcing the tetrahedra to be regular and thereby forcing it from a 7 one-dimensional letter code to a 2-letter code, because you can construct the entire QSN with just repeating copies of a Fibonacci chain. But you really can't do that with the projection of E8 to 3D. So it is our, I mean, if you want to say, what is the most novel idea we have? None of my ideas, like every single idea I notice that I have, is usually an independently discovered thing that some other woman or man has discovered and written about, but not this one. This thing is the single cipher of the mathematics that we have in a code theoretic view, because how we deal with geometric frustration combinatorially explodes the encoding power for some given quantity of choice actions in the QSN.
Yeah, in a way, the density, the connection density rank increases, from the curved space to this twisting space.
Right.
Because the vertex actually splits.
Right. It's like a flower, lotus flower. So if you imagine a flower and at a vertex, all these petals, and then the flower rotates open like that, and the vertices splay apart. So these 20 tetrahedra, which are regular in Elsner-Sloan, you project them down to 3D, and edge contraction occurs to keep the 12 vertices. And so when we force them to be regular, we open up each vertex by a factor of 5, like a flower opening up.
Yeah, this is clear, but just one second to finish this. This is clear, but to me, both these things, like the inability to tile a two-sphere and the increase in efficiency, are consequences of the same thing, which is how the projection does. It's not the efficiency is a consequence of the fact that you can't tile on the two-sphere. So for me, these two things are both consequences of what the QSN is, not one derived from the other.
Well, are you sure? Because
I'm not. That's why I'm asking.
Well, I know you're familiar with the paper you helped edit on the geometric frustration, and essentially, by choosing one isomorphism of spatial curvature expression over the other, we choose twist instead of edge contraction. By choosing that, which is the compound and rotate process, what we do is that expression of geometric frustration is exactly what explodes, is what opens the lotus flower.
On one side, and on the other side, you can't tile it on a two-sphere.
Two-sphere, what do you mean, a tile, a two-sphere?
It's the previous slides that Klee was showing.
Geometric frustration, I said one example of geometric frustration is that you can't tile tetrahedra on a two-sphere. That's just an example.
Well, tetrahedra is 3D, so you can't tile a two-sphere, of course. You can, analogy is a triangle. Triangle can tile a two-sphere.
Yeah, so my question was, how is that a cause for increase in efficiency? That was my question, because to me it seems like both these two things are consequences of the QSN itself, but not one.
Well, I think it means the tetrahedron can now tile the R3 space, so that's why that's why the projection, down from 4D to 3D, it has to do something. It has to maintain the regularity. So either you distort it or you have to twist. And
that is twist,
clear. Yeah, that twist somehow. Yeah, I mean that's not the direct reason, but it's a consequence.
That's what that was my question in the first place, because I didn't see what's the causal relation between not being able to do that and increasing efficiency.
Right.
Both of them seem like consequence of the exact
no,
same
it
process.
is still a consequence. For example, if you tried to do something like this with tetrahedra in the Elsner-Sloan, you couldn't, because they can tile the three-sphere. And it's the fact that they can't tile these spherical volumes in 2D, which is exactly the reason why you must either let the edges contract and let the tetrahedra become irregular, or where you get less information, or
right,
do
that's
the
why
twist.
the efficiency is not a consequence, because the consequences are, you can have the distortion, that is the one consequence, right? And you can do the twist, that's just another.
Yeah.
And this one has less efficiency, this one has higher efficiency.
Right.
So efficiency itself is not like a direct result, right?
Yeah.
Like
in order to increase the efficiency, you choose one.
Right.
I guess you're probably right,
it's,
Cynthia.
yeah.
What I mean to say is it's deeply related, meaning it's this inability of tetrahedra to do this in 3 space that really requires you to deal with it if you want to get more connection density.
Yeah, now it makes it makes sense.
Interesting about the SC2 theory, because you can map to the projective Hilbert space of the simplest quantum mechanical system, 2-level quantum mechanical system, qubit. So in some sense, the geometric frustration is a quantization of allow use to quantize the rotation inside the qubit space.
Right, this form of geometric frustration, right?
Yeah.
This twist form.
And the other question, what is the most efficient way to navigate in this to the Hilbert space? So we have to get the question of efficiency and the quantization of this Hilbert space. So the 2 spheres is foundational.
Yeah, for that, building on that, so he mentioned the projective space, but going back to the Reggie calculus,
Yeah.
when we were discussing this defect, right? You can equate some kind of defect angle
Yeah.
with
The deficit angle.
deficit angle, yeah. Deficit angle with a quantum of curvature. And you mentioned there's a relation to a splaying of vectors. So when you go back to projective spaces, so there's this concept of what usually comes up in terms of D-branes, where there's this coincident configuration that becomes, so they're overlapping, right? So you can think of it as coincident root vectors, right? So as soon as these spread apart, these D-branes, so this is the smooth picture you could think, there's a mass generation mechanism, which is a Higgs-like mechanism for these D-branes. So the analogy here would be something like a splaying of root vectors, and that's mass. So if you see a splaying of vectors and it's going along with, I mean, if it's going hand in hand with this kind of deficit angle, then the quantum of curvature is related to mass generation.
Right.
Yeah.
So you know, Fong calculated the isomorphic Reg calculus or the deficit angle with, so in loop quantum gravity, they have an infinity of possible deficit angles, right? That because again, it's a smooth concept. It's smooth mathematically, right? Like a spin foam is smooth mathematically within two bounds. There's an infinity of other values that it can take on. So if we wanted to convert our formalism to a Reg calculus related formalism, we would be extremely restricted, because in a good way, code theoretically restricted, because we have only a plus and minus value of this deficit angle. So
yeah, and there are this result of quantum computation that we are talking about codes that do computation. So you have that just with the qubit, with like in this case the projective Hilbert space, the two sphere, and one rotation, like one operator, you can do universal computation, quantum computation. So yeah,
I didn't know that. Cool. All right. So did we read this slide yet? So as discussed, the highest connection density, so the highest connection density occurs when you reduce your set of letters, your one-dimensional letters in the E8 to 3D projection, or the Elser-Sloan to 3D projection. You reduce those 7 letters of 1D length to only 1 and 1 over phi by forcing the tetrahedra to be regular, and then you bump up significantly the connection density, and you get your high regular symmetry, H3. So the binary bonus in the QSN that does not exist in the Elser-Sloan quasicrystal, which is a chirality syntax freedom, unless we find out that there is no syntactical freedom of the chirality. But if there is, then that will be a bonus binary value that acts multiplicatively on all the other coding elements to create an exponentially more powerful code, even though it has a lower valence rank than the Elser-Sloan. Because even though we have degree 60 vertices, we don't have an average valence rank that's higher than 57.5, which is the Elser-Sloan's valence rank. But we have these other qualities. Like for that vertex, there's a mirror set with a different 60 outside connections, and then there's the 3-5 periodicity and all this stuff that I'm mentioning to you. So it exponentially, not additively, adds to the encoding power of a network like the QSN. So this is deeply represented by Metatron's cube, which is just a symbolic geometric idea of juxtaposing with the same centroid lower symmetry objects in the crystal symmetry group, such as the cube, the tetrahedron, and octahedron, and cube octahedron, with shapes of the higher H3 symmetry, the icosahedron and the dodecahedron, and the icosahedron. So when you nest those all together in a kind of Russian doll structure like Metatron's cube, you have a real magic phenomenon. In other words, the forcing of the tetrahedra to be regular, crystallographic locally, and then in composite groups be H3, quasi-crystallographic, is the magic, well, not magic, it's the first principles math, really, that explodes our combinatorial encoding abilities of the QSN, plus jacks up the average valence rank. But it's not just the average valence rank, it's these extra binary things, and this, like the mirror symmetry, and then the 3-5 periodicity patterns, where you can alternate in helices, 3-3, 5-3, 5-3, 3. You can make Fibonacci word patterns.
I'll just say a quick comment. So it looks like in 3 dimensions, you can have deformations, you're saying, right? So in 4, everything's pretty regular, but you can have these deformations occur in the network, which are like error codes. So these error codes would be allowing some kind of gravitational.
Yeah, I mean, if we want, we can work with errors deliberately. Like we can allow errors in our Fibonacci codes, and then we can have some notion of error correction. There's something called the fast Fibonacci, error code correction. There's a lot of power for computational error correction schemes with Fibonacci, with Dirichlet integer-based things. Okay, so, and the syntactical freedom allowing for encoding, as I said, that with the 3-5 periodicity Fibonacci words adds yet another one-dimensional code set that also acts combinatorially with the others. So I am incapable of calculating all the interaction of these various binary, Fibonacci codes. But even though I can't calculate it, I can roughly see with some certainty that the combinatorics exceeds code theoretically the encoding power for some quantity of binary actions in the Elser-Sloan quasicrystal, plus you have to punish the Elser-Sloan for its extra dimension, as we argued before lunch. So the QSN, therefore, I conjecture, is the most powerful encoding scheme for topological quantum nets in graph drawing theories where one of your requirements, besides the non-locality, is regular symmetry, because with the regular symmetry, you can recover gauge symmetry physics. If you allowed just any quasicrystal of arbitrary irrational projections, that infinity of quasicrystals would not have the important high H3 symmetry that I fully expect to be necessary to connect by first principles to gauge symmetry physics. Okay? So 3, and the last reason that the QSN may be more powerful than the Elser-Sloan is that it lives in a lower dimension, which I said, we discussed. Recall that we measure connection density by using a logical metric and then volumizing it to an arbitrarily large volume and then counting the connections. So if you have 10 connections in a, so I don't want to go over this again. You guys are clear on the reason for that simple equation for measuring connection density with d dimension as your denominator. So the starting axiom that led us to the principle of efficient language was our result of this choice that all physicists must make. Nature is inherently random, or nature is code theoretic, and that is why she is non-deterministic, not because of the first simple answer. Presuming nature to be code theoretic follows from the deduction that reality is information theoretic, since it is difficult to imagine information not having its expression in code. Once we realize from the math, as Mia Hughes showed us when she visited, that energy is information, according to strictly respecting quantum mechanics, we have to now define information. Emergence theory defines information as code theorists define information, which is meaning or pattern, in this case physical pattern, conveyed by symbolic language, in this case self-referential geometric symbolism. And spatiotemporal languages, such as quasicrystals, may do a good job at conveying the meaning of our physical world, that is, simulating it. The reason we choose code theory over randomness is because code theory implies free will. And this is not a metaphysical or philosophical discussion about free will, because it's important. Because if you used to live 100 years ago and still believed in a Newtonian clockwork universe, and if that was the status quo belief, and then you claimed that you had free will, the physicists of the day would have said, well, you really don't. You're just a deterministic algorithm playing itself out in some destiny. But today, because of randomness in quantum mechanics, the majority of physicists surveyed believe they have free will. So although it sounds new age, today's modern physicists, because of randomness being inherent in their view, say, well, it's because of randomness that I have free will. I believe I have free will. So John Conway, the famous mathematician, and his co-author Koken proved rigorously that if it is true that humans have free will, if this physicist who thinks he has free will, if this is true, then particles are not random and have a form of primitive free will. And it's a complicated proof, but my understanding is that it's rigorous.
Yeah, but it's model dependent.
As everything.
As all proofs are.
Well, wait a minute. His is just purely mathematical, just FYI. It's a pure math logic, not a physics paper. Like Conway's pretty much like mostly a hardcore mathematician.
I looked at that paper and it has a series of assumptions.
Yeah. All right. So, you know, I mean, every single thing that one can say has a counter-contrarian, you know, way that you could say, but it might not be true. And I realize that, you know. But I'm trying to take you through a set of reasonable deductions so you can follow the flow of why I am risking my time and life on this approach, this program. And you guys are too. So I want to evolve it even further with you. This deduction, where we could be wrong. Anything, there could be a hidden assumption somewhere that just was a wrong assumption and that it sent us off on a meandering path. But so far, the reason I'm going so slow in this presentation is because I want to be slow so you can say, all right, the lesser of evils. It's probably more true that we have free will than we don't, in one's opinion, in each individual's opinion. But maybe we're not free. Maybe there is no free will. Whatever free will is, if it's true, we are massively influenced. So it's free will under enormous influence from the past, from the future, and from all non-local parts of space-time and every being in it. This huge constellation of influence. And within that, there is free will. But the Code Theoretic Axiom allows you a less than philosophical, a more rigorous discussion of free will, because at the end of the day, all language has a concept called syntactical freedom. And whether it's a bird language, a whale language, some coder writing in C++, or my English code that I'm speaking now, every time you get to a choice, you must make a legal, syntactically free choice according to the desired message that you're trying to convey. And if you follow the code legally with your syntax and make non-strategic choices, then your fully English legal or C++ syntactically legal code becomes noise. It ceases to do the function that languages do, because languages are three things that do one thing: finite set of symbols, ordering rules, freedom within the rules, choices within the rules, for the purpose of conveying information, meaning. So I observe humans to have free will. Any observation is a matter of opinion in experimental physics, but that's my opinion. And there are those who look at the same actions of humans and have the opinion that they do not have free will, which happens to be a minority of opinion among physicists because of randomness. That really gives them logical permission to believe in free will. So, if humans have free will, it cannot be playing out in a deterministic algorithm. So we need a code theoretic view. And it seems difficult to reconcile the idea of free will emerging from randomness compared to free will emerging from a code theoretic formalism. I know that people argue that free will can emerge from randomness. It's just a little less natural, whereas code theory, it just demands it. Like you can't even operate the code without choices that you have to do with some conscious intention to produce meaning.
Why can't, and just to be the devil's advocate here, speaking of, why can't a code theoretic be deterministic?
Because codes, by definition, are a finite set of symbols, ordering rules, and syntactical freedom. If you leave out one of those things, if you have an infinite set of symbols, it's not a code. If you have no syntactical freedom, it's merely a deterministic algorithm playing itself out. So
you're making this clear distinction in between a code and a deterministic algorithm.
Yeah, but it's not. I don't think it should be controversial. It's certainly not my definition. It's a definition well known that I have established. But there may be, yes, codes have
the trick here is when the code is playing itself, when the code is operating itself.
Right.
Because this is where you discuss syntactical freedom. Well, if you don't have anyone who's coding saying hello world over and over and over again, I mean, that's your syntactical freedom. While if you're inside the code playing itself out.
Yeah. So what happens if you have a cellular automaton and you've connected, you all know what cellular automata are, yes?
Game of life.
Yeah, Game of Life is an example. There are 3D examples of cellular automata, and it's a general notion. It can be very complicated. One of the things that's well known about cellular automata is that from extraordinarily simple rules and objects, after many iterative actions, surprisingly, I mean, Stephen Wolfram makes a big deal about it in 1,100 pages of a new kind of science, but surprisingly, all of these different patterns that are reminiscent of physical things come out in these 3D and 2D cellular automata. Now,
so can that be called as a code?
So it's
deterministic.
So in order to operate a cellular automata, Stephen Wolfram and all of the people in the community, they attach the syntactical freedom to a random number generator, which randomly selects the syntactically free steps in the cellular automata.
But do you have to?
Oh, I'm sorry. No. The cellular automata are deterministic algorithms. Sorry, let me go backwards because I'm going to tell you about an experiment we did here that I told Stephen Wolfram about. So the cellular automata are deterministic algorithms playing out, and they emerge out to complicated, surprising patterns. So I wondered, well, what happens if you take a standard cellular automata from Stephen Wolfram's book, right, where he's sort of standardized this general set of 256 cellular automata? And what happens if you insert what I called at the time a random hinge variable? So that in the step where there was something that says, if A, go to B, deterministic, you instead say, if A, go to B or C, right? You insert a hinge variable, and then you attach that hinge variable every time it comes up in the formerly. So in other words, if you alter a deterministic algorithm with a hinge variable, you convert it into a code because you've introduced syntactical freedom. So I wondered, well, what would happen if you inserted a hinge variable into one of the fundamental cellular automata. And this was like 6 years ago. So we did it, and we coded that, and we ran it over a large set of iterations. And what we got out was a pattern that was just as complex as the pattern run without the syntactical freedom, but it takes a lot of iterations before you see these beautiful patterns. And so that proved the conjecture or the suspicion that I had, and I told Stephen about that, and Stephen said, I know, we did that too. So I said, oh shit, I thought I was telling you something you didn't know. And so, yeah, so
that didn't prove, like, do you call the cellular automata also code?
No, I first started saying that, and then I had to remember what we did back then. Cellular automaton is generally a deterministic algorithm.
Right, I know.
But,
I know it's a deterministic.
But if you insert the hinge variable,
it sounds like a code to me, and also produce.
How does it sound like a code? In what way?
Well, I mean, it is a code.
In what way?
In what way? I mean, you have rules. Yes. And then it follows rules.
Where's the syntactical freedom?
Well, I don't know where the syntactical freedom.
You can insert it, and then it.
No, no. You don't have to. I'm just saying. I don't think, or I don't know why you think a code, the definition of the code has to have syntactical.
Well, we better
freedom.
get clear on that, everybody, because that's what we do here at QGR. We have
but that's
to get
your definition. I understand, but I don't know.
Yeah, but
I
let's
don't know. People
drill
can,
into that.
Yeah, but people can have different opinions. Like some people could say, like for example, Stephen Wolfman can argue that it is a code.
Yes, right.
And it also produces really realistic, complicated patterns. Why do we have to have some hinge variable?
So here's what we can do. We either get
code.
references or find an expert like Stephen. I've been thinking about this question for 9 years. The question of what is the definition of a code came up first with mathematicians like Garrett and Julio, and this has been discussed. But every one of you, I need you to make sure you argue with me if you disagree, but use references. Find out why you disagree. A code is strictly defined by syntactical freedom. Where there is no syntactical freedom, it is called a deterministic algorithm. And it's written in code, which might be part of the confusion. You write deterministic algorithms with code, like C++. But that doesn't mean it's written with code, okay? But the actual thing that the code under the hidden level simulates in a case of a cellular automaton in a computer is itself a deterministic algorithm. Okay, so is a cellular automaton by necessity a deterministic algorithm? And the answer is no, and I didn't discover that. Stephen Wolfram said, we've already done that, and you're right. If you insert a hinge variable, it's true. You get the same, even with that syntactical freedom taken away, in other words, the conversion of a deterministic algorithm to a code by the insertion of syntactically free steps.
It does not make it more complicated. It does not. It does not enhance anything. So why do we need this syntactic freedom?
Good question. So, great question. So we've had a lot of 100 years to really get comfortable with the idea that there's some experimental evidence demonstrating that nature is inherently non-deterministic. And the core thing about deterministic algorithms is, by definition, they are deterministic. And so you got to look to Bell's theorem and then Elaine Aspect's, experimental demonstration, and then the whole conversation in the community over the 100 years. And then make your decision. But I am suggesting to you that anybody who goes through that process will come out the other end saying, okay, reality seems to be non-deterministic. All right, so in this, so difficult to reconcile free will with randomness, a little bit easier to reconcile it with it's the stuff. And in this case, the interconnection of all things physical across time and space would cause, in John Conway's discussion, would cause the free will actors that he supposes to be real, or says that if you suppose free will to be real, the free will actors are causing everything else in the universe to be less than random. It is influencing everything. And I really think it's beautiful to realize by first principles that if we're serious about building a spin network on the QSN, right, either as ordered sets of the QSN or in the action horizon, you have this idea that the empire wave field, of discretized, quantum field from Mike Rios's empire field from when he was 3 years old and when he is 80 years old, that is impinging upon me now by first principles. Without a bunch of smooth space-time models, it has to, those empires reach through the sequence of shells and inform the probabilities, right? It defines the energy landscape. So think about the sort of superposition of an enormous quantity of empire waves, all in this wave, this discretized empire wave quantum field theory, and then realize, oh, well, that is none other than the energy landscape, classically, and none other than the quantum energy landscape, quantum mechanically. It defines what every particle's probability is at any time, too, for where it will be, because what defines probability amplitudes is the quantum energy landscape, right, with higher probabilities. And what defines our probability energy landscape is the probability of trit savings or trit cost, the probability of repulsion or the probability of attraction. So we're going to get into that more. So anyway, this is the essence of Conway's proof that I just said. So, and even excluding the idea of free will, we can look at Mia Hughes' quantum mechanics derivation that energy is information. And then if reality is information, then what processes that information? How is it organized? And what is the code within which it flows? So Shannon information exists where messages are conveyed by codes. And many authors have shown how Shannon information is equivalent to Boltzmann's physical information. And this is interesting to me because if Shannon information is always in the form of code, which it is, and if physical information is equal to Shannon information, then it seems strange that physical information would not be in the form of code. Besides, information is most rigorously defined, in my opinion, as meaning conveyed by symbolism, including self-referential symbolism. So does Boltzmann's information exist in a universal code? Does the quantum version of Boltzmann's information exist in a universal code? So when it comes to the question, that earlier question of A, reality, the fundamental stuff is randomness, or B, the fundamental stuff is syntactical freedom, because it's code theoretic, it seems that B would be more logical if nature is made of information. It's really not as complicated as one would think upon first looking at this code theoretic axiom, this kind of thinking. Boltzmann entropy counts only the raw bits of information, after all. And this is like taking the 30,000 sentences in the Bible and randomizing the letters down to just disorder, and still having the same amount of Boltzmann's information or quantum information at the fundamental quantum information level. You have the same amount, but all the emergent information will be lost, and whatever the power of that emergent information was to self-organize this continuingly off-equilibrium universe would be gone, because you would lose the emergent information that acts as a force. So quantum theory generally counts only, quantum theory generally doesn't talk a lot about emergent quantum information, such as all of the many, many forms of emergent quantum information, such as entanglement networks and all sorts of other objects in quantum emergent information. It does, there's a lot of people working on it, but it's super difficult to attach any good cataloging of the different strata of complicated, complex quantum systems information. Like it's difficult to work with. Like how do they explore the space of complex quantum information strata? They work with it, but to quantify one strata or another, it's very difficult. And I believe it's a little bit less difficult with a code theoretic way of thinking, where, like Mike said, you can take your strata and you can at least realize that the strata, the higher they are up, okay, the strata, you know where they rank on the strata because it's simple. DNA is made of other objects that are more simple and so on. So you can kind of take your your self-referential symbols, and you know where they rank. Now you don't know how to attach a magnitude exactly to each one, to each strata, but you can rank them, and you can use category theory formalism maybe for that. But my point is that modern materials science dealing with strongly correlated quantum systems, like nanocluster physics, where you get these strongly correlated systems, they're dealing a lot with the gauge symmetry and exploring the equations and really getting into the nitty-gritty, but they're not really doing too much with this realization that others have written about on how emergent information begins in special cases to profoundly act like a force instructing the system how to further evolve in an off-equilibrium state. So code theoretic quantum mechanics, that is emergence theory, or for example, emergence theory. On the other hand, here we deal with the property of emergence as a really important thing, which is a property of all codes and languages. And emergence, not emergency, is part of the very definition of symbolic languages. You cannot suggest any symbolic language, not even Morse code, that doesn't have emergent symbolism composed of the base symbols. So we can use the same letters as quantum mechanics, or we can use the Boltzmann's letters, his microstates, right? The unique classes of parallel vectors. And we don't have to worry about quantum gravity for this thinking, for this kind of code theoretic thinking. You can apply it to any kind of formalism, and it's helpful. And still arrive at the code theoretic axiom, which is just nothing other than complex systems theory, where simple things emerge to more complex things, wherein the complex things loop back to instruct the behavior of the further evolution of the system. So we just take fundamental things as letters. So one microstate self-organizes in Boltzmann entropy in certain cases of off-equilibrium thermodynamics with other microstates to form the first primitive complex system at strata 2, and then it just keeps going. So, but what both quantum mechanics and classic theory fail to account for, usually in a rigorous way, is the power of emergence or emergent information as a force and how powerfully it acts on other objects. So I hope today you're starting to get the feeling for why we call what we do emergence theory. It's at the very core of code theory. So when we allow our Boltzmann's microstates, W, or quantum mechanical analogs, to self-organize into the code of DNA or into an entire human being, for example, such systems instruct other particles outside of that system. In other words, take DNA, and it's in some environment, imagine it to be in your body somewhere within a sphere of a diameter that is 1 angstrom. And within that volume of that 1 angstrom sphere, you have a lot of other simpler molecules. You have a bunch of free electrons. You have photons. You've got all sorts of, you've got some free atoms that are not part of molecules. You've got other simpler molecules. You've got all this stuff, right, and this mass energy. And in that volume, okay, if you just restrict yourself to that angstrom volume, where the DNA is in there. The DNA is just acting as the dominant coordinator instructing that mass energy how to behave, down from the fermions to the bosons to every composite emergent structure. It is the king of organization. So you can say, wow, right there in that small spherical area, the magnitude of power of this raw information of this 4-letter code with these protein folding algorithms and all these instructions is just, it's just remarkable. So you can kind of appreciate the brilliance of Heisenberg, who realized that it has to be a quasi-crystal molecule in order for this information to be encoded in it. And I'll talk more about Heisenberg later. So DNA, with its vast code, as I said, just possesses far more influence over matter than a randomly organized connection of the exact same quantity of base information or energy. So, the DNA in that sphere is acting like the man in the control tower at an airport who orchestrates the behavior of 100 different airplanes in a radius of space far larger than the control tower room. So in that domain, the control tower guy at the airport, he is moving mass everywhere, controlling it in a coordinated way.
So quick question. Could this be used to direct mutations? Can it be used to, say you have random mutations, right, quote random, but maybe they're not random. And this computation could be used to survey which one would be more favorable.
Yeah, it's a good idea. Well, we know that, we know from the literature that evolution on the biosphere required quantum tunneling in DNA. It's a bread and butter fact of modern, people who study this. And so you, therefore, wouldn't be here if it wasn't for quantum mechanic tunneling of DNA, because nothing would have speciated.
Then the,
right?
The replication defects is...
So replication defects?
And the DNA, for it to replicate and then like change a little bit?
Yes, but that mechanism of action is known to require quantum tunneling. And the quantum tunneling is a probabilistic event and spontaneous. But the deep thing is, wow, so can intelligent signals acting as strange attractors through this spatiotemporal permeation of all of microspace from the Empire wave quantum field from the future, can it somehow gently steer the quantum probability amplitudes? And if it did it ever so gently with enough iterations, it would draw itself towards the strange attractor, which is a future state of evolution, without being detectable, because it can be very subtle and occur over millions of years and just be a subtle thing. All it takes, right, to take a system into some chaotic phase, as we know, is just the tiniest perturbation, like the butterfly effect. And so, because it's quite remarkable that this conversation exists, emerging from a quark-gluon plasma, this conversation, it's almost against all odds.
This is highly improbable.
Yeah, it does.
Unless you can probe the future.
Unless the universe for that original quark-gluon plasma, it couldn't have existed in a self-actualized version of cosmology unless the system were able to self-evolve towards unimaginable complexity capable of self-actualizing itself from this abstract code that it holds within its consciousness.
Could you use empires for that?
Well, you can never get away from the empires, because there are all forms of empires. I think there are topological empires and classes of empires that we haven't even discovered yet. It's like a principle of and by the way, we show you empires, Fong usually, we look at certain empires, but empire is a generalized thing. There's an empire for every constellation. There are other empires that exist across shells. So the evolution in the deep future of a universe where some godlike levels of consciousness eventually emerge, that is connected into us in every microscopic volume, that intelligence, with this first principles, like very mathy first principles idea of the empire wave domain, the transtemporal empire.
Each of the strata has their own version of an empire.
It runs through. So for example, take the QSN and go shell 1, 2, 3, 4 to 20. Okay, so you have empires running this direction. You have empires running perpendicular to the shell directions, or to the shell. So the empires, and then all of it, you have to think about as this field. Yeah, like this waving, non-noisy field. And the field itself is the quantum energy landscape, right? So
DNA could possibly use the empire field for smart genetic mutations.
All I can tell you is DNA is built out of the golden ratio, and if you want lossless communication between something at 23 orders of magnitude greater than the Planck scale, then if you suppose that the Planck scale, you've got this Dirichlet integer kind of golden ratio based quantum, graph drawing spin network, and then you want to have a molecule like DNA be able to talk to it, right? Then, or if this empire field is really the fabric of that QSN at the Planck scale, which it is, then you want to follow the geometry. So you want, if you're nature, you would want to self-organize a molecule that's capable of interfacing with this empire field in a very high-resolution, lossless way, because the system needs strange attractor actions from the future. Then you would organize it with the golden ratio. So DNA has two helices that are offset by a golden ratio value, which is a higher ranking pair of sequential Fibonacci lengths, because it can't be precisely the golden ratio because they're at atoms, right? So you can only get Fibonacci numbers. And of course, the Fibonacci numbers have a world record, which is they approach their limit at the golden ratio faster than any other convergent sequence. And so it uses that, and then it takes one helix, which has perfect five-fold symmetry, and then it rotates the second helix relative to the first by a golden ratio rotation, which is 36 degrees. So and then if you start looking at the spacing and studying it really carefully, because of the construction, you see that it's a quasi-periodic molecule built of the golden ratio. So Erwin Schrödinger was thinking one day, and he said, wow, nobody's discovered whatever this molecule that encodes life is. And this was in the early 1940s, because DNA was discovered in 1953 by Crick and Watson. So it hadn't been identified. So he was thinking, wow, so that's a lot of information that this gene must be encoding. So they knew for decades that there was this mystery gene. They hadn't identified it. And he said, so, wow, there's only really three ways that we can organize things, which is periodic, or completely disorderly, or aperiodic. And he said, well, it can't be disorderly because you can't really encode information in a disorderly thing. And it shouldn't be periodic because it seems like that's just too simple. And so he was thinking code theoretically back in 1947. So then he wrote in his famous book, What is Life? He said, it must be a periodic crystal, right? So he might have said quasi-crystal, but it wasn't until 1975 or so that Paul Steinhard coined the word quasi-crystal. And so anyway, and it's not necessarily a quasi-crystal as we think of it, which is generated by cut and projection. But it is a quasi-periodic crystal indeed. That's what he said. So I think he's a genius for just realizing this in the 1940s, this kind of code theoretic view. And deeper than that, that was his big argument for negative entropy and the ability of something like this emergent code in this aperiodic crystal to be able to instruct matter how to ever more self-organize into complexity with protein folding algorithms and whatnot. So I would like to if I could go back in a time machine and meet him or Schrödinger, I guess I would pick him. But plus, he's the father of quantum mechanics. He's the one who invented the matrix approach before Schrödinger converted it to the wave function. So, all right. So anyway, so DNA does what what the guy in the airport control tower, moving coherent patterns of 100-ton airplanes or 100,000, huge things. So DNA does this with an emergent strata that's very far up the emergent hierarchy beyond strata 1 and beyond Boltzmann's information, beyond fundamental quantum information. All right, so if someone asks, well, hey, you guys at QGR, what is the deepest thing that makes this emergence theory you guys are talking about so interesting, right? Then I would say, well, it recognizes emergent information to be a force. A force is something that instructs mass energy how to behave, how to self-organize. So previously I said it seems B would be the logical choice, which is code theoretic if nature is made of information. But that's not the strongest argument that nature is code theoretic. The expression of any code is always a hierarchical stack of strata of emergent meaning. Okay? For example, the binary language encoding a movie on a DVD starts at strata 1 with bits, which are the conserved letters. And those conserved elements may or may not be organized into words called bytes. And then it can go up another 8 strata in the coding scheme for a typical movie, before it gets to the rendering on your DVD player. And so all languages in full expression have this quality of emergent symbolism in a hierarchy. And this is the exact same empirical quality that nature has. In other words, I'm saying the code theoretic, forget everything I've said all day, and realize that nature is already in a strata of hierarchical structure, where the higher you go on the structure, like DNA or humans or certain protein catalysts, they begin ever more to inform the complex self-organization of some off-equilibrium system in special cases. And that is a code theoretic idea, emergent structure, emergent self-referential symbolism. So nature uses simple rules at the core of things, whether you see that as quantum mechanics, classic physics, or some new quantum gravity physics. And inside those rules and allowed degrees of freedom, so we have these degrees of freedom in quantum mechanics, which are probability, are non-one probabilities. The letters as quantum or classic bits begin to self-organize into hierarchies where every strata in the hierarchy has a greater magnitude of power to influence its environment by pure information acting as a force. So the point is that it's trivially true that nature self-organizes letters into words and words into sentences, etc. And nature is behaving code theoretically by this empirical observation of things like 81 stable elements emerging from quarks and electrons up to DNA, this English code emerging way higher up the hierarchy that's vibrating in this room into your ears. So is this English acting as a force instructing matter how to behave the way a protein folding algorithm in DNA does, or is it just vibrating the room and shaking things about? That's not a big deal. DNA with its protein folding algorithms, that's a big deal. Well, yeah, kind of, because the meaning encoded in this organization of letters that I'm pronouncing as words and vibrating your eardrums with is instructing correlated patterns of entanglement in your mind, in your brain, dipole orientation patterns, signatures that are topological, according to neurobiologists, enormous strata of unknown and some known levels of coherent pattern just by vibrating the air. Whereas if I vibrated the air in a meaningless, random way, it wouldn't do that. It wouldn't create those structures physically in the same way. So it is instructing the order of countless bosons and fermions throughout your body as you contemplate your particular meaning of each word and its association to your beliefs and memories. It's changing your hormonal balances in subtle ways. So if reality is made of code theoretic information, does it compute that information? Is reality a computer? Is your brain a computer? Well, it's certainly something that computes, because I can compute 1 + 1. So I'm a computer. But am I really a computer?
Well, that's what they used to call them before electronic computers.
Mm-hmm. So they called the humans, right? Computers, right? So, but nowadays we have a kind of common definition of a computer, which is something that it's a machine and you put inputs and it gives you outputs and it's deterministic. It doesn't invent questions. It doesn't invent problems. It solves problems, computes them. But I don't think I'm a computer just because I compute, unless I were in World War II and I was a computer, like those women that they made compute things, right? All right, computers don't generate spontaneous questions or have free will. Neural networks do. And they compute too. So neural networks are allowed by physics because a bunch of them have emerged in this room through the laws of physics. Neural networks can have codes based on self-referential symbolism. So any artificial neural network theory that has ever been developed has a code, and the human neural network should have a code, although it's too complex. We know it's topological. It's too complex for anybody to have ever derived the code. It's a very opportunistic area of science right now, is to understand how the brain works. So for example, your brain is a neural network and it has some unknown natural net language that science hasn't discovered. And what kind of code is this supposed network language? Well, for one thing, it would be a spatiotemporal code. And this is because as a physical neural net, its building blocks are the same space-time building blocks of physics. It is a neural net instead of an artificial neural net, which is at first abstract before anything else. The artificial neural network formalisms are this kind of abstract thing. But your particular neural network is made of, it operates with resonances and phase, and it's built of angles between, molecular angles. It's a spatiotemporal code. In other words, it's a self-referential symbolic code at some kind of level, where the base symbols are made of quantum information or classic microstates, if you want. So from there, those simpler things self-organize into proteins in your brain, and then those self-organize into the neural network of your mind, which is known to behave topologically. This is very, very exciting to get new papers that show that the brain is acting as a topological net, and it's a quantum topological net. And it's also recently known this last year that the signatures in your brain with certain thoughts mathematically map to certain hyperdimensional solids. If anybody wants to see the reference on that, just ask me. So here, the code in your mind is playing out in a network in 3 space that's made of all 81 geometric shapes as the stable atoms that we know of, which are themselves made of simpler shapes at a lower scale, and which compose to more complex shapes or symbols like DNA at higher scales. So the Code Theoretic Axiom and the PEL provide the rationale for why the universe uses self-referential symbolism, and then the observation of complex systems in emergence, which is just simple, is sort of some good evidential ideas that might support the idea of the basic principle of code theory, which is emergent structure, emergent action from the emergent structure. So in this kind of view, both the code and the simulation are one and the same object, where the hardware, the software, and the simulation output of the quantum neural network itself in your mind are all the same self-referential symbolism, geometric symbols representing themselves. This is Ray's. Never want to take that quote from you, Ray. That's your quote. All right. So because quasicrystals have syntactical freedom by mathematical first principles, they are self-referential symbolic languages. And conveniently, they happen to be inherently non-local. And by virtue of being languages or codes, they are strictly non-deterministic. A special class of quasicrystals derived from any Lie lattice that encodes standard model particle physics gauge symmetry would be a logical choice to start exploring. So you use some lattice like E6 or E8 that had work published where people have derived gauge symmetry physics, at least for everything except gravity. And you kind of start with that to narrow things down. And for example, you wouldn't want to start necessarily with a lower dimensional lattice like Z3, because there hasn't been as much good gauge symmetry physics done on that. So, and the dimension for such a quasicrystal code should be carefully chosen by Einstein's edict, which is be as simple as possible, but not too simple. And so we reject 1D and 2D on the basis that we presume reality plays out in greater than 2 spatial dimensions. And this leaves us with either 3D or 4D, because we do not have a 5 or greater dimensional analog of H3. So there are no appropriate quasicrystals in dimensions greater than 4D. And I'm not going to defend that here, but I do have things to say about why I say this. But I can tell you that the defense relates to the fact that there are no analogs, as I said, of H3 and H4 in higher dimensions. So I'm pretty certain that mathematical quasicrystals, more broadly defined, are the only case of non-arbitrary or first principles-based symbolic language where Fong has defined the syntactical freedom by the first principles of a finite set of cut window translations relative to some empire window. So what is a must for a graph-theoretic quantum gravity code? It must be inherently non-local by geometric first principles. And if we were trying to build a gravitational or classic physics simulation, we would actually have a massive universe of codes to choose from. We would not need the class of codes that are local. That is, we wouldn't need the quasicrystal codes. We could use other kinds of graph formalisms or other codes. But if you have to have a non-local code by first principles, you might be stuck with the irrational projections of higher dimensional lattices unless somebody has, unless I find a counterexample. So the deep non-locality of nature requires a non-local code. So now you can arbitrarily, of course, invent a non-local code by just plugging the non-local statistical behavior of quantum mechanics into some abstract formalism. And then you could call that a non-local code. But it would not be a non-local code by first principles. Quasicrystals are by first principles. So it's reasonable to say that any fundamental or non-arbitrary geometric system, such as the E8 lattice, has a rather elegant algebraic analog. And the principle of efficient language seems to demand that the algebraic reduction or analog to any graph drawing code must be, again, with quotation marks, maximally efficient, which is something we'll drill into because there's ways to discuss the algebraic efficiency. But first, what else besides non-locality is a must-have for this code dual that includes a geometric and an algebraic isomorphism? All right, so what else besides non-locality, right, is a must-have for this code? Symmetry. Symmetry. You have to have symmetry in your projection. The gauge symmetries must be deeply recoverable in the algebraic and geometric analogs. Along with the restriction of non-locality, symmetry restrictions are going to reduce the set of possible codes by an infinity down to a much, much smaller set that leaves you with only 2, the Elsner-Sloan quasicrystal and all sorts, and the 36 vertex type generalized, the 24 vertex type generalized, and then the QSN. and there's nothing else, there's really nothing else in 4D that competes with the degree 57 density of the Elser-Sloan. So now we've gotten rid of an infinity, because remember, you could take just E8 and you could do an infinity of irrational projections, each one being a different quasi-crystal. And then you could do the same thing, right, with E6. There's another infinity. So we've cast out this infinity due to symmetry, because we know a little bit about how the gauge symmetry physics correlates to, you know, the group theory, and we know how to induce these higher groups from the icosahedral group and 600 cell. Like, we can see all these relationships, and we can know that algebraically it's the most compact, and we know that as we rotate from infinitesimal rotations of our special angles, we explode the quantity of letters, that is, the irreducible one-dimensional letters. We explode them. So you can build the Elser-Sloan quasi-crystal with just 2 letters. But if you infinitesimally deviate from that rotation, you'll explode the quantity of letters. So, and you lose your symmetry, which messes up your elegant gauge symmetry algebra. So, as I said, quasi-crystals are the only non-arbitrary mathematical codes by geometric first principles that I have seen in the 9 years that I've actually been looking for a counterexample. By way of review, any fundamental lattice and its associated algebra is non-code theoretic, although I know that there are algebras in lattices, but I only mean this in a really restricted way, Mike, which is that if I take, let's say, the cubic lattice in any dimension, and I say, how much syntactical freedom do I have on organizing my cubes? Then you would say, absolutely none, right? You have to organize it exactly this way. And if I say, how many fundamental building blocks do I have? And you'll say, 1. It's just 1 unit length. But with a quasi-crystal of some small size, you can tell me, well, you have all this syntactical freedom. You can explain the rules to me and explain the syntax, and then I can play. I can do it how I want. So anyway, that's what I just explained. Code has to have 2 or more objects with syntactical freedom within the ordering rules. So the A, E, D, and Z series of fundamental lattices are in this way that I describe codes by building blocks and organizational rules and syntax are not codes. So only upon irrational projection of slices of such lattices to n minus m dimension projection do we get codes with 2 or more fundamental building blocks or prototiles and syntactical freedom. And due to the first principles of the transdimensional projection itself, these codes are inherently non-local. As Elaine Cohn's powerful quantum gravity approach writings show with his non-commutative geometry, he often says the Penrose tiling is the quintessential example of non-commutative geometry. And he's not the only person who uses non-commutative geometry, of course, for unification physics, quantum gravity. Planes in the quasi-crystalline spin network contain subsets of points that are the Penrose tiling. So we have non-commutative geometry all over the Penrose tiling as these networks share points and cross one another. So where the Phazon dynamics of a Penrose tiling code can be described with matrix formalism, the point-sharing interactions between Penrose tilings in the QSN as 2-dimensional subspaces within the H3 symmetry space of the QSN can be described as a tensor network formalism, right? Where you can take each of the 1-dimensional chains in each Penrose tiling and correlate that with a Dirichlet integer-based matrix, and then you can relate all the other matrices of the other 1-dimensional Fibonacci chains, and you can see how a change in one matrix like spans out changes in all the other matrices. So it seems certain to me that tensor network formalism would be inevitable for us, or I mean, there'll be other formalisms, but I really suspect that tensor network is going to be the most computationally economical for us to deal with this. So specifically, the QSN is just an interactive network of dynamical Fibonacci chains. And the eigenvalues describing the quantum behavior of a dynamical Fibonacci chain can be described with the Dirichlet integer-based sequence of matrix operations. So restriction is really good when it comes to code theory. So I want you to think about this. Imagine I have a matrix set of eigenvalues that describe the sort of freedom, right, in a Fibonacci chain. Okay? Now cross that with another Fibonacci chain that shares points and several others, and realize that the interaction of the different tensor networks restricts the eigenvalues. The interaction itself of all of us is restricting behavior. So it's kind of cool to me that the expectation I have of tensor network interaction is going to curtail or restrict the behavior of the individual Fibonacci chains if they were otherwise operating with eigenvalues just all by themselves without interactions. So restriction, of course, is a good thing. It's a good word when it comes to codes. You want to have the minimal set of syntactical freedom, simple, and the minimal set of symbols, simple. And then you get powerful general codes and algebras. So the more restrictive, the smaller your symbol set, the smaller your syntactical degrees of freedom and solution sets will be. That's your coding power. Your coding power is greater with restriction. So C algebras are one of the deeply implied algebraic isomorphisms to quasicrystals by both quantum, and they're used by quantum mechanics experts, and they're used by people who work with quantum gravity. So C-star algebras, it's beyond my pay grade of understanding deeply the formalism. But at least I understand that C-star algebras are deeply associated with non-commutative geometry, and C-star algebras are very powerful for quantum gravity and other quantum mechanical approaches. So there are many works on this. As I said, it's known that you may or may not know this, C-star algebras are inherent to the rich mathematics of quasicrystals. So note that any irrational projection of a finite portion of an n-dimensional lattice to n minus m dimensions is a quasicrystal. So until a decent counterexample or a counter logic can be found that weakens my guess that quasicrystals are the only first principles or non-arbitrary case of non-local geometric codes, because I claim that geometric self-referential symbolic language, which can be reduced to one simplexes connected by zero simplexes connected by one simplexes in a graph theoretic formalism on some possibility space in algebra, tensor network formalism defined by what I call AB equals P solutions, which those solutions are going to obey the principle of efficient language in terms of efficiency, where efficiency then is reduced to the energy landscape where particle probabilities go to lower energy wells in the landscape. And here for us, the low energy well is defined by code theoretic economy called trit coincidence or trit savings, where a step or an action can express a step for two or more empire waves simultaneously, thereby saving a step and resulting physically in an attraction. So that's your energy landscape, and that defines the probability amplitudes of some span of AB equals P solutions, right, which are isomorphic to Fang's finite set of cut window translations. In other words, all of Fang's cut window translations will not have the same probability amplitude. The probability amplitudes are defined down here in the spin network, which self-referentially expresses the energy landscape, the quantum energy landscape, which is built of empire, non-local empire fields. So I hope you're seeing how these kind of things are like kind of describing one another and seeing a picture emerge. So how can we narrow the infinity? As I mentioned, symmetry is how we're going to narrow it. You take the E8, you project a slice to 4D via one of an infinity of irrational hyperprojectors, but only one irrational projector gives a regular high symmetry. There's another projector that'll give you a cubic symmetry as you projected, a crystal symmetry. That's a lower symmetry group. You can't do as much gauge symmetry physics on it as you can in dimension 4 and 3 with the higher symmetry object. So you either go to the high dimensional space and you take a crystal symmetry group and you can do great gauge symmetry physics there, or if you're desperate to have a lower dimensional space, you have to have the higher symmetries to get your same algebraic power for physically realistic gauge symmetry. So and that is the one that generates the Elser-Sloan quasicrystal with H4 symmetry, this one and only one projection. But it has different directions. So you can project, it's like a cube, how you could project it, to a hexagon along one of 4 different projection body diagonals, yeah. So of course there are, as I said, several identical hypervectors on E8 that will all give you the H4 symmetry, but they're just different ways of pointing the same set of angles in your hypervector. So gauge symmetries, I'll explain this. So H4 symmetry corresponds to the cyclic permutations of the regular polytope in 4D called the 600 cell. And of course, the algebraic analog of that notion of regular or semi-regular symmetries corresponds to certain operations that are closed under multiplication and division, or that express unity. So it's very powerful for the gauge symmetry to use the H4 or H3 symmetry. So this can also be related to the idea of closed Eulerian and Hamiltonian circuits or paths through identical edge connections on the surface of such polytopes, where you kind of can understand a geometric version of how the algebraic paths are economical and closed. So we have reduced an infinity of irrational projections that it could have been down to just one, okay? And so how can we reduce further this set of choices to argue or defend to others what would be the optimal quasicrystal code? And we can do a dimensional elimination. We talked a bunch about that. And we know that nature plays out in 3 space. Well, we don't know anything. We might use some arguments to argue that we measure 3 spatial dimensions, right? And so at least there's experimental evidence, not proof. And we know that any n-dimensional quasicrystal is reducible to a network of 1-dimensional quasicrystals. And we know that, as I said, nature seems to play out in 3 space. And we know that any n-dimensional, oh, that's a repeat. So again, repeating, we eliminate that. That leaves us 3D to infinity. And we know also that knots can only exist in 3D, not 4D, not the Elser-Sloan space. And that's kind of fascinating because knot theory might tie into unification physics in a deep way, along with its related braid theory. And there's countless papers arguing over the last 100 years about how knot theory and braid theory deeply tie into fundamental physics. So at least you get that opportunity if you want to use knot or braid theory or knot theory in the QSN. You don't have that in the Elser-Sloan. So the golden ratio is the only fraction that's closed under multiplication and division within the, that has this quality. It's fractally self-identical, okay, where the ratio of the long part to the short part is the same as the ratio of the sum of the long and short to the whole. And that fractal self-identical nature, which is unique in the universe of all fractions to the golden ratio, has super convenient economy at an algebraic level where it switch hits, like it can do things under addition and multiplication that are so economical that no other number has that quality algebraically, and it boils down to the uniqueness of its fractal self-identical quality here. So, and it has a powerful consequence when attempting to create an n-dimensional code of one-dimensional codes, spatial codes, with the same species of letters, which has the highest connectivity rank or density of connections possible in non-local networks. So of course, we could take something like the Z2 lattice, and we can connect every point to every other point in the Z2 lattice, to generate high density. In other words, take a point, draw a line from the next point to the next point to the next point, just keep drawing, for each point, draw a line to every other point in the infinite Z2 lattice such that your average vertex density is infinity, okay? So you can do that. But the question that we're discussing as we eliminate infinities of different graphs is not, well, what is the network or the graph with the highest average valence rank? That's not our question. Our question is, what's the non-local or topological quantum network with the highest average valence rank and connectivity density that we defined early? So if we desire this non-locality to be based on first principles and not just creative plugs, then we really have to use irrational projective geometry. So we're restricted to that. So, and if we desire, as I said, to correlate it to gauge symmetry equations, well, then we have to use a geometric analog of a higher Lie algebra and use only the hypervector that transforms or brings the projection to the highest symmetry rank, regular symmetry rank in the projected space. So now it is beyond the scope of this talk to explain why one cannot get a quasi-crystal in 4D with a higher average valence rank than the Elser-Sloan quasi-crystal by going, for example, to the E100 lattice and then just projecting that to 4D. As I'm not going to get into that, but you can't. You just want to use, if you're trying to get that 57.5 average valence rank in 4D, and that's the highest in a non-local net, that you don't,
57 fluctuate to 57.5 or 56.5, so it's around 57.
So it may be. So it seems like it's 57. So yeah. that's that deep thing. So thank you, because I thought it was fluctuating between two other numbers. I read the email too fast. So listen. So just I'm not going to explain this, but for anybody who just wants to take my word for it until you find out for yourself. E8 is a limit in this sense because you can't get this density that you get in Elser-Sloan, 57, if you project E7 or D7 or Z7 or Z8. So, and you can't get any better if you go to E9 or E1 million. So E8, which is the optimal sphere packing in 8 dimensions, uniquely gives you this highest average valence rank in R4. But I'm still going to state here anyway that going to a higher dimensional analog of the E8 lattice isn't going to get you anything better. But I'd like to take a minute to explain why the average valence rank is highest when the projection itself possesses the highest rank regular symmetry, while deviating from the H3 or H4 decreases your valence rank. So for example, one can project E8 to 4D and get a lower symmetry 24-cell symmetry with a lower average valence rank. And we know that the highest symmetry regular is H4. And using the near neighbor distances as your metric, the projection to the lower symmetry has a density that is distinctly lower than in the projection to 24-cell symmetry, right? So we can use that same method. So let's just use a projection of a finite portion of Z3. So we take this tiny portion of Z3, which is a cube. Yes?
No, I said 20. Oh, okay. 15 would be ideal. Sorry.
So we're projecting this small portion of the 3-cube lattice to the plane. It's not creating a quasi-crystal. It's projecting to a crystal. But it's the highest regular symmetry possible, right? Because another projection could give you a square, right? And that has a lower symmetry than this. You can't get any higher than this.
It's the one of the sphere packing.
Yeah, that's the maximum sphere packing in R2. So now here we project the cube to the plane, and then we're getting this 6-fold symmetry. But part of what defines this highest symmetry, if you notice, is that we have homogenized or reduced the quantity of edge lengths. So every edge length is 1. Now, notice that an infinitesimal deviation from this exact projection angle will separate the coincidentally projected 2 points here at the center. And that will break apart this degree 6 vertex into 2 separate degree 3 vertices, thereby lowering the average valence rank or connectivity rank of the projection. And this fact is described by or generated by the homogenization of the transformed edge lengths. So that an infinitesimal deviation along an irrational direction this way, okay, will explode the 12 edges of the cube that are now unit length into exactly 12 separate different edges. Now, if you go along this direction here, you'll explode it into a smaller number than 12, but greater than 1. But an arbitrary infinitesimal rotation will bring this to 12 separate edge lengths. So you can see that the edge length reduction and the symmetry, right, are both, the regular symmetry, are both related in this really simple example to the coincidence of the convergence of 2 lower degree vertices to become a higher degree vertex in the projection. Now let's turn our attention to a projection of a finite portion of the E8 lattice using the same projection hypervector, which generates the Elser-Sloan quasi-crystal. So here we're projecting part of a Gaussian polytope to 3D. Now a certain thickness of the cut window on a single Gaussian polytope cell of the E8 lattice to 3D will actually generate a superposition of 2 600-cell projections to 3D, where each is scaled to the other as the golden ratio, and where the center point of each 600-cell projection is coincident with the center point of the other one. So you get that idea of convergence again, right? Because each of the 600 cells, when they have the center point in the projection coincident, then you double the valence rank. So an infinitesimal deviation from this angle will separate the coincident points, reducing the connectivity power and average valence rank of this finite-sized quasi-crystal. And again, the unit edges will change from the minimum code theoretic limit of 2 symbols to be which is code in this case of 1 and 1 over phi, to a very large set of different lengths. So it's the reduction to the limit of 2. Now we have different lengths here. We have 7 lengths, but when you start crossing the Fibonacci chains with one another, it starts...
That's because it's a projection to 3D.
Yes, it starts chopping the other lengths in half and making smaller Dirichlet integer lengths. But so it's the reduction to the limit of 2 in H4 that allows the connection density and the average valence rank to be highest. So in summary, for this section, I am suggesting that the quantity of edge lengths must be minimized in order to generate in order to generate 2 qualities in E8 projections to 4D. Because you can construct the entire Elster-Sloan quasi-crystal with only 2 one-dimensional letters, 1 and 1 over phi, and you build out the entire thing. Fibonacci chains. All right, so regular symmetry in the projection, we have to have that. Highest average, regular high symmetry, H. Highest average valence rank, and therefore the highest connection density, as calculated how we agreed was a good way. E8 can be projected to lower regular symmetry here. And we have a low valence rank. And then it can be projected to higher symmetry where we have a much higher valence rank. This thing can be constructed with 1 letter, right? And this has to be constructed with at least 2 letters.
So that's 2 lengths on the left one.
Yeah, but they can be understood to sort of cross. In other words, if this was your unit length, you could see that unit length here, here.
Yes, but there is a diagonal
and then
at least 2. But the other has at least 7, no? Many more than 2. At the right.
No, Ray, so
right
Ray,
picture.
so what happens is when they start crossing, you start chopping your fundamental Dirichlet integer lengths into shorter lengths.
Yeah, so that's,
Like a
there is
deflation
not 2 lengths here, there is
but
many more.
But we're talking about compose, so there's more than 2 lengths in the Elster-Sloan quasi-crystal. You can construct it with just 2 lengths, where you allow the Fibonacci chains to overlap one another, and then as they overlap, they chop, they kind of create a kind of an idea like deflation inflation, where they chop it down to smaller values. So there's a video of somebody who's taken a Gossett polytope and he projects it to the plane, and he does a very slow animation along different arbitrary irrational angles, and it hits these primary angles, and you see all these points. They move around in circles. The points are like winding, and then they converge, and then they'll converge to be coincident, and then you get a higher valence rank and regular symmetry. Then it goes out. It's really cool to see that, to develop an intuition, of how special these projections are. And remember, the projector that transforms the Gossett polytope or the E8 lattice to the H4 symmetry or the H3 symmetry is a set of values that lives in one of the sub-lattices of E8. It's not introduced outside to get the regular symmetry. It's taken from inside the lattice, and it has an algebraic way to deal with it outside of geometry, where you're dealing with an E8 root vector algebra interacting with itself with one of its subalgebras. Again, with this portion of the 5-cube lattice, we have high H3 symmetry and a reduction of edge lengths to 2, where we chop the edge lengths in half to get deflations of the original 2, but where we can still construct it with the two elements, and we get the convergence only when it's regular, and only when you have a reduction of the edge lengths. So code theoretically, you always want to try to reduce yourself to if it's a spatiotemporal code, for example, you want to restrict your freedom of your oscillators to the code theoretic limit, which is 2 near neighbor distances in a network of energy wells, or if it's a temporal code, 2 as a Fibonacci beat. If it's a computer code, 2, right? You want to get to 2, Morse code, 2, right? And by going to 2, geometrically, right? Forget the code theoretic efficiency idea. Geometrically, you get special qualities. It bumps up your density rank of your connections, and it brings you into regular symmetry, high symmetry. And again, I think I said the QSN can be constructed with only 1 over the golden ratio. One big uber takeaway message from all of this, I think, is that the QSN appears to me to be an incredibly powerful code, and so far, by all these different arguments that are deductive, not necessarily fully conclusive, it seems that it would be difficult to imagine an H3 symmetric space in R3 of higher encoding power than the QSN. It has degree 60 vertices. And then when you add on to that, so just without the adding on of the 3-5 periodicities and the helicity binary operator that multiplies, even without that, it seems to have the highest average vertex rank by first principles without just drawing arbitrary extra lines, which will break up your first principles non-locality and break up how you're relating it back to the algebras higher. And it seems that the Elser-Sloan has a higher average valence rank, but a weaker, but a penalty for its dimensionality. And because it can handle tetrahedra and tile them differently, it doesn't have the lotus flower concept with tetrahedra that we discussed, where you have a binary chirality sign value, and it doesn't have this same thing with the 3-5 periodicity. Remember, the 3-5 periodicity itself comes from how we treat geometric frustration, where if you have some helix and you create a step which rotates it in the same direction of the helix, you get 5 periodicity. And if you go the opposite direction, you get 3 periodicity. So anyway, the argument here loosely is that it seems, after thinking about this for a couple years, that the QSN may be provable as the most efficient non-local neural network code suitable for simulating gauge symmetry physics, because it has the H3 and because it has this powerful encoding, even more so than Elser-Sloan. And I want to try to assign somebody at some point next year to very rigorously explore that and try to use some of my thinking tools about defining density of connections, right, in a graph, and then go a lot further than I did and make it a mathematical proof and try to prove it formally. And if that could be done, then it would make news. Even if we never do physics on it, it would make news mathematically. So again, little I is our conserved information, and it can be any kind of information you want, either Boltzmann's information, Shannon's information, or an irreducible unit of quantum information.
The base level.
It's at the base level. These actions are the AB equals P solutions. These actions are the cut plus projection geometric operations. These actions are the spin network formalism actions. So measures of I on the QSN can be based on many things: tetrahedron selections, edge connections, on-off point selections, and so on. Regardless of what equivalent system we work with, I is conserved over n frames in some ordered set of possibility space state selections globally. E equals emergent information. E cannot be conserved, even in principle. I equals little I plus E, where E is very low, little I is approximately I, and where E is very high, I is greater, little I is greater than I. E grows...
The other way around, little I is smaller than I.
Yeah, that's right.
Where E is very high, I is less than...
Yeah, it's written correctly, but you said it the other way around.
Oh, thank you. Okay. E grows exponentially with rank in the emergent hierarchy, such that total I grows exponentially in complex systems. When I is high, it acts as a non-trivial force, eventually showing the second law of thermodynamics and naive views of quantum mechanics that traffic only in quantum information to fail. In this code theoretic physics paradigm, we can unpack the classic notion of energy and convert it to its quantum analog in the form, one quantum analog in the form of zero-point energy. We can then recover zero-point energy to a generalized class of discretized quantum field theories, of which emergence theory is just one case. Here, the old E equals our new I, the immeasurable E. Can we quantify E? No, for three reasons. Any sufficiently complex level of E, which is virtually all physical systems, is an MP problem. E at any strata possesses a non-local component, rendering a local measurer incapable of fully assessing it. Like what Cinziana said earlier, she said, how do you know, I think, she said, how do you know what system this is part of non-locally, right? It could be part of lots of other systems. So you can't quantify it so easily if you can't measure it. You can't measure it unless you're the universe, right? You have to be a non-local global measurer. So due to the fact that, one, any local system is part of a transspatial and transtemporal network of complex systems, and two, E cannot be conserved even in principle, it is untenable, that is, it's undoable, to arbitrarily select a cutoff for measuring the E associated with a local system. Well, that's no fun, because we like to measure things, right? So what can we do with E analytically in order to study it and exploit it for technology? Well, the first step in thinking about the physics of exploiting E in emergence theory is to synthesize some common concepts from Shannon's entropy, Boltzmann's entropy, information theory, and generalized language and code theory. So the common theme in this, one common theme running through all of these that can offer a possibility for synthesis thinking is the idea of noise, right? Faults, defects, noise, right? And the idea of meaning, or in Shannon's entropy, the quality of a signal, or the idea of information. So in classic thermodynamics, we have high noise and therefore low meaning, like low physical meaning, low emergence, with high entropy due to collisions driving an explosion of parallel vector classes which disorganize all of the I toward I being equal to little I. Noise. And then in quantum mechanics, when a system becomes chaotic enough, its non-local quantum correlation, which is a form of quantum E, can drop so low such that I is approximately equal to little I. Noise. So, however, the only time in quantum mechanics when I equals little I would be in a volume of vacuum space near 0 Kelvin, where the ultimate disorder of the Dirac sea of virtual bosons and fermions expresses Planck scale noise. So in that case, your system is so simple and so close to strata 1 that the total information in that volume between, let's say, 2 galaxies in some volume of vacuum space. Now, in our approach, this corresponds to local AB equals P solutions with one minimally small rank in the inflation-deflation spectrum. So I'll be talking to you guys tomorrow about how the AB equals P solutions are deeply based on inflation-deflation values. And the reason for that, if it's not clear, is when you think about a high entropy system that's very noisy, you have very high frequency collisions so that the vector, the length component of any vector is very, very small. And then when you discretize your idea of smooth motion in Boltzmann entropy down to the Planck time and the Planck distance, you're dealing in integer multiples of the fundamental unit length and integer multiples of the discrete frames. And so what happens is those little noisy, ultra Planck scale level type quantum foam, right, discretized quantum foam, those are very short, which corresponds to an A, B equals P operator. In the higher dimensional algebras, that corresponds to a very thin cut window. Now, when your discrete translations become larger, as larger integer multiples of the Planck length, what happens is your cut window thickness is larger. So an inflation-deflation idea maps to noise. And disordered sets. So this is the whole key to everything. It's the ordering of sets that are identical things that get ordered differently to create noise and ultra high level strata of E and everything in between. So in other words, the probability amplitudes for each P solution on each shell, which are just simply cut plus projection operators, but in algebraic form in a tensor network. So in other words, these probability amplitudes for each P solution on each shell that are defined by these discrete translations of a cut window relative to an empire window are all equal with no peaks. Peaks in your probability amplitudes require an interesting energy landscape. But where your energy landscape is so homogeneous and noisy like the Dirac sea in vacuum, then what happens is your probability amplitudes that in a normal physical energy landscape would have big peaks, your energy landscape goes homogeneous, which takes your probability amplitudes in some finite set of AB equals P solutions to sort of flatten out the probabilities. So we restrict and lens probabilities in this tensor network by the definition of the energy landscape, which is the discrete quantum field theory defined by empire waves, all interacting and overlapping. So this noise is such that all the information of this space of vacuum in the Dirac sea is pretty much equal to little I. And in Shannon's entropy, noise in codes degrades the information content of a signal. In general, code language theory in general, noise includes things like poor use of syntax in the form of redundancy, like my presentations, or or non-compact expressions that are not redundant, but they're not as elegant as they could be. Or noise can mean illegal syntax, defects, right? Breaking the rules, where the symbolism ceases to serve its purpose in conveying emergent meaning beyond just the base level of the meaning of each individual strata, right?
Can we stop there?
Yeah, this is, I've been looking at the clock, so this is good.
No, but I mean, exactly your last phrase, we already had discussion on that with Fang the last time, and I'm not sure we agree that noise, in terms of defects, is devoid of meaning.
But it's not devoid of meaning. It has level strata 1.
Yeah, which is base information, not emergent information.
Right.
So last time with your example, when you were saying when you run your data and you have your experiment goes wrong, that doesn't mean that you don't learn anything from it, that it doesn't have emergent information, because it can teach you how to 100 times of how not to run your experiment, which is in the realm of emergent information, is not base. And it's still...
So it would be a context of information.
Exactly, so can we...
Yeah, but I'm just saying, I was giving all these examples about Shannon entropy where noise degrades signals. I'm showing you a picture of a monitor. I'm just trying to create a general idea that in code theory, you can have noise or coherence. You can have poems that are concise, compact. You can have wordy, wasteful things. I'm just trying to create this thought for you. But Fang, if she is capable of watching this screen and getting all kinds of deep information.
Not deep.
It may be because she's creating that in the complex system of herself, you know?
Yeah, but that's not on this point of it being disordered. It's on the point of it being a defect. I'm not sure we agree with the fact that it's...
I don't know if we're going to have defects in our formalism.
Emergence or not.
Yeah, I don't know if we're going to even have defects in our formalism. If we need them, we'll use them. But I'm not sure we'll even need to debate about defects or not unless we use them. But yeah.